Okay. So anybody wants to share their screen and show what they did so that the others can also appreciate? Any volunteers? Nobody wants to volunteer? Okay, somebody has shared something. Let me copy the message and I'm not able to copy this message. How do you copy this message? So Dave has shared his code. Let me show you his code. Okay. Module comp. Okay. One feedback for you is comp is a very poorly chosen name. Okay. It may mean comparator, it can mean compensator, it can mean anything. Okay. So please call it two's complement. Okay. Please, all of you should make a note that if you join the industry, you can't give such names. Okay. And then bit stream in, okay, because it is an input. End of is in because it is an input. Clock in, reset in. So you have to make it a habit. Okay. The reason why I'm showing you like this by actually doing is to emphasize these things. Okay. Complement out. Okay. Otherwise, nobody will know what is the input and output. Okay. Input bit stream in, end of signal in, clock in, and reset in. And output 63 bit. Okay. Did I specify it is 64 bit like that, or do you have assumed it like that? 64 bit temp.
Yes, it won't.
Huh? Int I equal to 0. Indentation is very important, right? See, you look at the code which I was sending, right? Your code is all aligned to the left. Okay. So readability is very poor. Always positive edge of clock in or positive edge of reset in. If reset is there, then begin 0. Complement is 64. I 0 and else. If EOS is begin, Okay. So looks like you're actually storing everything. Mhm. You're storing the whole thing. See, this is not required. Okay. The algorithm that I explained in the class, I think maybe you have not followed. So let me try to explain it again.
Sir,
Yeah.
I have written one code where I defined one FSM
Hmm.
with two states.
Correct.
Uh,
That's the one. That's the
then
one.
with respect to reset and clock, I initialize the state. Then
Right.
depending on the signal, I
Mhm.
assigned if it is a bit zero, pass it.
Right.
The one, then go for it, counting.
Yes. Yes.
Rest of
Yes.
the bit complement it.
Yes. Yes. I
But I
agree with
had a problem like you were given 8-bit test case
you.
and 143-bit.
Hmm.
I have to change the code every time input and run to show the output.
Let us do it now, and you can tell me how it goes, right?
Yes, sir.
So, see, I think the point I was trying to make yesterday, maybe it was not very clear. See, if I have a input, so writing, just a second. See, suppose the number given to me is bn minus 1, bn minus 2, b naught. Okay. So, it's an n bit input. Given to me, least significant bit comes first. Okay. What I was trying to explain to you is, see, if the in this somewhere or the other there must be a one place where one begins, right? This is the place where the first one occurs, and all the others to the right are zeros. Okay. Let us say that occurs at jth position. Okay. So this is b naught, b1. This is bj minus 1, and this is bj. This is bj plus 1 up to bn minus 1, right? This has to happen. There must be some position where we will find a 1, right? So let us assume that it happens at position j. This is the first time we encounter a 1. Okay, all the others to the right are 0. So the 2's complement of this pattern is obtained by first calculating the 1's complement. So this is the 1's complement, that is bn minus 1 bar, bn minus 2 bar, bj plus 1 bar. This 1 will go to 0, and I will get all ones. So there will be j uh, there will be j zeros on the right hand side. Now the 2's complement is obtained by adding 1 to b bar. So b bar plus 1. So if I add a 1 to this, so all these guys will become 0. Okay, 1 plus 1. Okay, and I'll get a 1. And this will remain bj plus 1 bar, bj plus 2 bar, etc. all the way up to bn minus 1 bar. Is that clear? So the algorithm says start from the right, find the position of the first one, and copy all of this as it is. This one followed by all zeros goes exactly like this, and the rest of the bits are flipped. So it's a simple algorithm. Okay, so start. looking at the bits from LSB onwards. So two things can occur. If it is a 0, then keep outputting 0. If it's a 1, copy that 1 and then flip all the remaining bits. So another way to do it is like this. See, there is a state S0. This is the initial state. So this machine keeps looking at the bit stream, right? The bit stream equal to 0. See, the state S0 means I have not seen a 1 so far. S1 means, let us say, I have seen the 1. So if the bit stream is 0, right, then it will continue to remain in the same state because it has still not seen a 1 and it will output as 0. Okay, remember all the zeros to the right, yeah, just get copied. No, this 0, these zeros are copied here. So that is what we are doing by putting a 1, 0 here. The first time when I encounter a 1, maybe it's here, right? I will move to the state S1. This means I have seen a 1. So that bit stream equal to 1 will result in an output of 1. Because remember this 1 is also copied here. Right? And there onwards, we are simply going to flip everything. If I get bit stream equal to 0, I output a 1 and I remain in this state because I have already seen a 1. And if I get a 1, I'll flip it into a 0. Okay. So this is a state machine. So this is known as a state machine or 2's complement. See, it doesn't need any storage except for the this state. And if there are two states, we only need one flop. Okay, one D flip flop or something like that will be sufficient to implement this machine, right? So if you want to implement that machine, right, what do we have to do? We have to write the state table, right? We have to write the state table. So the state table looks like this. We always have to indicate what is the previous state and the bit stream value and the next state, right, and maybe the output value. So here, suppose I'm in state S0 and the bit stream is 0, I remain in S0 and output is 0. If I'm in S0 and I see a 1, I go to S1, output a 1. If I'm in S1, I see a 0, then I remain in S1 but output a 1, and S1 1, S1 0. So this is where, when we are complementing, and this is when we are copying. You can go ahead and design if you feel like, right? I mean, the Verilog, system. We are only interested in verification. So frankly speaking, it is not our job to design anything. But there is no harm in understanding how to design. So we encode S0 and S1. So one bit is enough, right? So we could try S0 equal to 0 and S1 equal to 1, right? So and then there are two outputs, the next state and the output. Okay. So draw corner maps for next state. So there are only two input variables, namely previous state and bit stream. So this can be 0 or 1, this can be 0 or 1. So our this table indicates that for 0 0 the output is 0 because state it remains in the state S0, and in all these cases it is 1, right? So you look at this, here you can see very clearly that S0 and all these are S1s, and we have chosen S1 equal to 1, so this is why it's like this. So what is the output NS equal to as a function of PS and BS? What gate is this? It is an OR gate, isn't it? PS plus BS.
Circuit.
Okay, it's an OR gate. Similarly, draw the Carnot map for the PS BS 0 0. I'm sorry, 0 1 0 1. This is for the output. So here 0 0 is 0, 0 1 is 1. Then 1 0 is 1, right? 1 0 is 0 1. 1 0 is 1, and 1 1 is 0. So this is a XOR gate. Right? So this output is PS XORed with BS. So if you draw the circuit, it will look somewhat like this. So this is the previous state, and this is the bit state. Okay. We are storing the a flip flop. Okay, it's a D input and a Q output. So this is the previous state. Can you mute people if you don't mind? And this is the next state. The previous state is connected here, and the next state is connected here. The input. And this is a clock. So when we reset the flip flop, see, do you mind, muting yourself whoever is speaking? The admin must take action. So this is the circuit that we can use. Okay, this is a gate level circuit that we can use. Okay, but I did not ask you to do all this. Okay, so if you didn't do this, don't worry, right? I did not ask you to do all this design, etc. Okay, so I expected a simple solution only, nothing fancy. The first thing is to write down a description. Let us say it's called two's complementer. Okay. Clock in, reset in. Okay, it's better to first give the clock and reset. Okay, then you can give your bit stream, etc. And then give the output. If you feel that there are too many inputs and outputs, you can even make an interface. Okay. Remember the interface thing we had discussed, right? So you should try to use all those things, right? This is, what is that will get you the practice that you require, right? So we could make a interface. Okay. Now let us describe these guys. Input, clock in, reset in, bit stream in, and UIS in. Then output is two's complement output. Okay, it will take time to type. Okay, but it is well spent. Time well spent. Okay, you will be thankful later. Okay, if you give names like ABC here, it may reduce the amount of typing you do here right now, right? But later debugging will be very difficult. Okay, then we have to do always. Okay, any sequential logic will wait for a positive edge of a clock or positive edge of reset. So this add syntax can be read as wait for. Always wait for either a positive edge of the clock to come in or the positive edge of the reset to come in. Okay. You can think of this as an event. Okay. We are waiting for an event. What is that event? Either the clock comes or the reset comes. And we can put always here and put always here. Then the first thing to check is whether reset has come. That always gets higher priority. Okay. This kind of a reset is called asynchronous reset. Okay, that means we don't wait for the clock. Okay, as soon as the reset comes, we take action. Some people will design using what are called as synchronous resets, where they don't check for this at all. They only wait for clock, and when the clock comes in, they will first check whether reset has come or not. Okay, there is a difference between these two. This what I have written just now is called as the asynchronous reset, where it is not synchronized with clock. So if reset comes, then we have to set the state. See, we have to remember the state. Let us enumerate variable. We can call it S0 and S1. If S0 is not very clear, you can say not seen any one, and have seen 1. So these are the two states: not seen anyone and or not seen one so far and have seen one. So these are the two possible states. So when the reset comes in, the state should be set to not seen one so far, because that is our initial state. There may not be any other thing to do as of now. Okay. Else means if the reset has not come, then we'll have to check for what the state is. Okay. So we could use case if you want. Okay. So we can say case state. There are two possibilities. One is not seen one so far. The other is seen have seen one. These are the two possibilities. See here also we may have to check whether the bit stream is 0 or 1. Okay. So if the bit stream, we could again write a case statement if you wish, right? Then it will be exactly like implementing the truth table. But you could also simply say if bit stream in equals 0, okay, then no change in state. State remains the same thing. If you want, you can explicitly say not seen. We may have to do two things. So put a begin here. So we have to first let the state be the same. And the other thing is output is 0. Complement two's complement output. Same thing here, right? If bit stream in equals 1. Oh, I'm sorry. I forgot the else part, right? Else, if it is not 0 but 1, then we have to move to state equal to have seen 1 and output is 1. Here, same thing. If bitstream in is 1B0, then we remain in the same state. We don't have to reassign the state again. It is just for documentation purpose. It sort of brings out that we remain in the same state. Okay. Then 2's complement out will be 1B1. Okay, we are flipping the 0 to a 1. Whereas if it is not, again the state changes are not there, and 2's complement out is equal to 1b. Okay, so you don't have to repeat this again and again, okay, because you are not changing the state. Similarly here, you didn't have to do this because the state is already not seen one so far. Okay, so even if you comment these out, it should work. Okay, what we have not handled is end of state. This guy will continuously keep on converting, right? If you want to handle the end of state, maybe you can handle it here, right? If not end of state, okay. If Okay. If end of state has come, then we can sort of go into the end state or something like that, right? So begin, end. So this is when it is not reset. Okay. That is, the clock is what is being handled. So if end of S in, then we could sort of set the state to done. Okay. So we can introduce a done state. Okay. And else, okay. Else do all of this case. So we can maybe make it like this. So this is how we could do it. Maybe there are many solutions. This is not the only solution. Okay. You could do it in any other way. There may be minor variations of the same thing, right? Then to test it out, we can write 2's complement test. Okay. We'll have to incorporate one, we have to instantiate one 2's complementer. Call it as instant of 2's complement. And there you'll have to tie in all the signals. So let us have clock main. We can have it either bit or clock. Okay, it's up to you. If you don't think X will ever come, you can use bit. Bit clock in, clock main, reset main, end of S main, and bit stream main. So these are our input signals. And the other things that we need are bit 2's complement. Okay. And here we have to tie in everything. Dot in is tied to clock main. Dot reset in is tied to reset the main. Dot bit stream in to bit stream main. Dot EOS in to EOS main. Dot complement out to 2's complement. So we have made the hardware connections. Right? See, can you please mute yourself, whoever is speaking?
இது part 1 part 2 அது part 1 sir plus 2 இது plus 1 single
Hello?
plus 2 ல தான் தமிழ் இது clear
சார் வரலீங்களா?
இப்பதான் வெளியே வந்துட்டு வெளியே போனேன்
சரி. நல்லா இருக்கா?
நல்லா இருக்கேன் சார்
லீவ் வந்துட்டு போய்
ஆமாங்க சார் இப்ப அதான் அந்த ஏசிஎஸ் அது கிளியர் ஆகலைங்க சார்
See, admin, can you mute them, please?
ஃபவுண்டேஷன் கிளியர் ஆயிடுது அந்த இன்டர் இது எழுதுனாங்க ஒரு பேப்பர் சரி அதனா அவன் விட்டுட்டான் ஏன்னா அங்கேயும் ரொம்ப நீங்க சார் பாருங்க ராமத்து சர்டிஃபிகேட் பண்ணிக்கிறேன்
முடிச்சிட்டு வந்துட்டேன்.
ஆமாங்க சார் இப்போ இன்டர்நேஷனல்
ரெண்டு மூணு ஸ்டேட்
பண்ண முடியலன்னு சொல்லுங்க
சரி.
இதை கண்டினியூ பண்ணிக்கிறேன் ரெண்டும் முடியல
Admin, are you not able to mute them?
அதுக்கு நிறைய இருக்கிறாங்க சார் அங்கே வந்துட்டு
பிரைஸ்
இப்ப இல்லாம So PSBBs. No, administration. Then
Okay. So the test bench is going to be here. So we can send a random signal maybe, or we could send a signal for which we know the output. Okay, so for example, we could say int random number. Okay, so int signed or whatever, int signed random. So we could initialize that. Okay, to some new random range. Okay. Minus let us say minus 100 to plus 100. Then we will connect the minus 100 to 100 means, or let us say minus 128 to 127. Okay, so this is the 8-bit range. Okay, so now we'll have to give the zero, 1 bit at a time. Okay, so for example, we could say random number of 0 is equal to bit stream. So the 0th bit of that random number is being connected to bit stream main, right? And then we'll also reset so we sent a pulse on reset, and now maybe we can send end of let us make end of s main to 0 and clock main also to be 0. Now we'll repeat whatever number of times, 8 times. Okay, because we want to we want to try to find the 2's complement of an 8-bit number. Okay, repeat 8, begin, end. So this means repeat all of this 8 times. So we'll first make clock equal to 1, then we'll make clock equal to 0. Okay. And then at the end, maybe we can make we can make end of s equal to 0. So the last one is where we will make end of s equal to 0. I'm sorry, end of s equal to 1. Right? Or we can do it here. So one more clock pulse, right? Just for the case of end of s. Okay. Then what do we have to observe? We have to observe the 2's complement out. I think we have forgotten to connect this. No, we may have to say assign to complement out. To complement out. No, we are already doing that. So we may have to declare it as reg. Okay. We are already setting it here. Okay. So we have to just display that value to complement. So that is the one in the main. Okay. If you prefer, you can call it tools complement main. So hopefully this will have everything that we need, right? Okay. So try. Okay. We forgot to change the input. No. See, before we bring in the next bit, we must right shift random number. So random number equals random number. See, we are connecting always zero bit, right? So random number zero is what is being given to this two's complementer. So when we right shift, the next bit will come in. So that we had forgotten. So this is a random number we are giving the first 8 bits. So but this is not worked out, no? It was supposed to generate 128 to 27. I don't see why all of them are zeros and ones. Anyway, display random number equal to percentage v random number. Reset main is 0. Clock is being okay. So this should just keep right shifting. Okay, if things have gone well, it should just keep right shifting, which is happening. Say 0 1 0 0, 0 1 0 0 1 0 0 0 0 1 0 0 1 0 0 0 1. So it is right shifting correctly and feeding the right bits. So the bug is possibly on the right hand side. Use complement out. AOS main is 0, right? Let us make sure that the state is all correct. So let us verify that the state is correctly going. So the state changes have not happened at all. So the bug could be how I have defined the state as an enumerated data type. So maybe when the reset comes, has the reset has gone okay. Then end of signal is initially 0, so it should come here. If it is 1, then say if it's 1, okay. See, let us try using that EP wave, okay, to see and if we can debug this. So we'll try dollar dump file dump.vcd and dollar dump was 0 inst to complement. Okay. So this may help us in understanding if something is happening. See, the state has always remained same and at the end becomes 2. See, initially it never changed state. It always remained 0 and then went to done state directly. So 0 is not seen a 1. Okay. 1 means seen a 1 and 2 means done. So bitstream is not changing at all. So bitstream is a problem. Okay. So bitstream never changed. Okay. So that is our bug actually. So we'll close this. Yeah, I thought I have connected random. Oh, you know what? I think I had to do this again. This thing has to be done again. After shifting, we have to do this again. Otherwise, it doesn't get. So that was the bug. So now you can see the state shifted to 1 as soon as the first one came. Okay, bitstream became 1. After that, state became 1 and never, it always remained there. And 2's complement out is initially 0, right? And then it became 1 and then whenever the input change, it becomes, so it is complementing. So 1 means 0, 0 means 1, like that. So that's what it is. And till as long as reset is why is it undefined here? Okay, it should have become maybe we have to do that explicitly,
Till first positive clock edge it is undefined.
huh?
Till first clock edge comes.
It is still we should have
Initial value.
maybe we should initialize that also.
Yes.
Okay. So you know what, this is begin and so as long as the reset is there, it is not defined. But when the reset becomes high, it gets 0. Okay, and this is the output that we get. Okay, so the input is 0, 1, then 0, 0, 1, and then 0, 0, 0, I think, and then again. Okay. So we can pause this. We can read it in the. It's easy to read it in the text output. Okay, so text output also would have come here. Okay, so it has only done this part. So we are not interested in these bits. See, I think what we should have done is we should not declare random number as a integer. So we should define it instead as a bit 7 to 0. Okay. So that would avoid all this confusion. So you can see that the input was 0, 0, 0, 1, 0, 0, 1, 0, and the output initially is 0. This one. Okay. Then this one comes as it is. Okay, the very first one. And after that, these two zeros are flipped here. And then the next one is flipped here. Hey, is it correct? 0, 1, then 1, 1. How it's okay. 1, 1, 0, correct. Then 1, 1, 1. Okay, I think that's okay, right? And yeah, any doubts here? We can also try to take the output that we are getting and capture in the so we'll keep another bit signed 7:0 uh, converted
Sir, why
Initially,
sign is taken, sir?
I'll tell you. It's a two's complement number, so we have to take it as a sign number. Okay. So otherwise, it will treat it possibly as an unsigned number. Okay. So bit. Oh, this is bit. Not big.
Sir,
So
in
we'll
your
try.
sir, in your design only you are checking the bits and taking action for two's complement. Then inherently, why again you would come?
Yeah. No, I think I'll explain. Just wait for me to complete. So converted number is 0. Okay. Then the numbers that are coming out, okay, we'll put them in this one. So converted number equals to complement out main and converted number 7 to. Okay. So I'm shifting in the two's complement output and shifting out. I'm right shifting the two's complement. So at the end, okay, we can display both. See, this will not display. It's too much display. Here we can display input equals percentage B, output equals percent. Random number is the input and converted number is out. Okay. So let us run this through. Oh, that random number would have got changed. Huh? We are shifting it everywhere. So this input I should print it here itself. Hmm. See, this is the random number we took 0 0 0 0 1 0 0 0, and because we can went on shifting it, it became like this. But you can check this and this. Okay, so 0 came out as 0, this 1 came out as 1, and everything else got flipped. So 1 1 1, then 0, then 1. You can try instead of a random number. So suppose we try percentage D. Okay, let us see what happens. This I should not percentage D. I should not do now. So initially the number was 18. Okay, this number is 18. And this number is minus 8. See, this is the reason I declared it as signed. Okay, professor who asked me the question,
Yes, sir, understood, sir.
you understood, na?
Yeah.
This way I'm very clear that it is changing, right? Let us change instead of a random number. Let us say random number equals -1. Okay, so this means all ones. Oh, I shouldn't do this waveform business here. So you can see that output. Why is it 2, man? Output not be 2. Oh, okay. See, unfortunately, we are initializing this to 1, 0 now. That is causing the problem. See, this 2's complement number initialization is causing the problem. It's not doing that. Let us try -3 and see what happens. So there is a bug. Okay. So the case is here. If it is a 1,
ನೀನ್ ಬುಕ್ಸ್ ಬಿಸ್ನೆಸ್ ಸ್ಟಡೀಸ್ ಎಲ್ಲ ಓದೋ ಎಂಟನೇ ಜೊತೆ ಬುಕ್ಸ್ ಎಲ್ಲ ಇದ್ದಾಕಿಲ್ಲ ಅಕೌಂಟ್ಸ್ ಬುಕ್ ಎಲ್ಲ ಫುಲ್ ಬುಕ್ ಎಲ್ಲ ಅವ್ರಿಗೆ ರೆಫರೆನ್ಸ್ ಬೇಕು
there is one bug. Okay.
ಅಕೌಂಟ್ಸ್ ಬುಕ್ ಇರ್ಲಿಲ್ಲ ಅದು ಅತ್ತೆ ಯಪ್ಪ ಹಾಕುತ್ತೇನೆ ನಾನು ಬಿಸ್ನೆಸ್
Madam, please mute yourself. What is the reason, man? We are getting one bit wrong. So when the last bit is 1, we have a bug. Okay. So when the last bit is 0, we will not have any bugs. So I'll show you. If it's an even number, suppose I say -4 or something like that, then I think it will go through. So output is 4. Okay, you can see. So input is -4, output is 4. Similarly, if the input is 24, it's an even number, so output will also be -24. Okay, so this is fine. The problem seems to occur when the input is ends with a 1. So here there is some bug. So when I'm in not seen 1 so far, if the bit stream is not 0, then I'm assigning it to 1. So again, it may be this way could be causing the problem. Oh, this is already okay. Let us give an odd number. It does not display the state. There's too much information. See, initially there is 0. I don't know how it is happening. What is the reason? I think I know. See, we are looking at the wrong timing, man. The timing is wrong. See, there is nothing wrong with the output. Okay. If you see the EP wave, you will understand my problem. Okay. So this is a very important point, guys. You should understand this. See, look at the output. Okay. I have given bit stream 1 in the beginning, right? And the output is actually 1 here. It's correct. Okay. The output is correct. But because I'm displaying it at 5, it's taking this old value. Okay. The old value is being displayed here. Okay. The 2's complement old value is being displayed here. So we had to change the, we had to see it at a different point of time. So, and another thing that happened very interestingly is we would have caught this bug if 2's complement out was declared as a logic. Okay, I'll show you. See, this is exactly what I wanted to tell you. Okay, see, suppose I make this 2's complement output as logic. Okay, that means 4 states. Okay, now see what will happen as the output. See, can you see the X here? That is the problem. We declared is a bit, so it is forcing it to 0. You understand? If we had written it as logic, this bug would have become evident. The bug is that we are looking at it at the wrong time. Okay. So when the clock goes from 0 to 1, immediately we should not look. We should give at least 1 minute of time. Okay. Then you will see that things will be okay. The observation also matters where you observe. Okay. Your logic may be okay, but your observation point also matters. Okay. See, now things are okay. This is 23, this is minus 23. Okay. And 2's complement is 1. Okay, this was a nasty bug. Okay, we unfortunately declared 2's complement as a bit. Bit is only 2 state, so the x became a 0. Okay, so that is why we were seeing a 0 and we were wondering what is going on. Okay, so I think this brought out a very important point. I tried to make the same earlier, but we actually saw it happening today. Did everybody understand this? Let me ask the people in chat. Where is the chat? I've not been seeing the chat. So, Dhruvang Patel, you understood what happened? There was a bug in our code. The bug was not really in the logic, but it was more in where we were observing the output. We were observing it as soon as this clock went from 0 to 1 and it was showing the old value. Okay. So, these are all small, things that we had to take into account. Okay. So, Agile also has changed the output. Yeah. All right. Good. Anybody wants me to go through this again? Don't hesitate. Huh? If something is not clear, I'll be more than happy to explain. Anybody wants me to explain? You should not hesitate. So, when you say yes, sir, does it mean that you want me to explain? Poonam Kadam, you want me to explain again? Okay. Poonam, sir, understood. Bhola Kumar Rai, does it mean you want me to explain or what? Okay. Okay, very good. So, I'll give you this code in case you need this later. So, Professor, you were saying something in the beginning about some 8-bit something you were saying. Is that clear now?
Sir, shall I tell what I had done?
You can tell.
I had initially just yesterday posted one like y equal to x bar plus 1.
Ah,
That's all. Tested.
no, no,
But
no.
I
See,
saw that question is saying that we
it's
are
bit serial.
receiving a bit of patterns.
It's bit
In
serially.
that, after detecting 8 bits, we
Hmm.
have to do the stop the logic and find out two's complement of that number. That's why I given 7 8-bit numbers to check. Then I
Hmm.
wrote a state message similar way. So
Hmm.
first checking the zero
Yes.
in one state. So if it
Yes.
is zero, then I'll go to the next state and check what is
Hmm.
the next bit it is.
Hmm.
So accordingly, I generated signal, but my problem happened like while testing, I declared a range. There I given the number, and
Mm-hmm.
whenever I have to test, it will work with declare the fixed size of the range. So
See,
if
what I
the
have done
size,
is, see, you can see how
uh,
I have addressed that thing. See, what
yes,
I have done is I have declared a random number as a bit sign, and I keep right
yeah,
shifting it. Okay, so that that
yes,
last bit goes into that two's complement. Okay, so maybe I can give a last bit of a random number goes into two's complement. That is how we feed the two's complementer. Similarly, converted number is assembled by left shifting the the so we assemble the converted number by left shifting the output of two's complement. Okay, so to sort of explicitly say what I'm doing, see what I have done is this. So I have built a module known as two's complementer. So this is my clock, this is my reset, and this is the bit stream and end of stream. So this is a bit stream. I have created an 8-bit register here, and the 0th bit of this is going into this. Okay, so this is what I have called as random number. Okay, and the output that is coming out is going into the 0th bit of that converted number. And I keep right shifting this guy so that the bits keep coming in. And similarly, I keep right shifting the this bit. So finally, this guy will go and sit here, and the whole thing will. Okay, is that clear to everybody? And again, like I said earlier in a previous thing, see, you need not display all this stuff. Okay, you can turn it off. And at the end, what you could say is if random number is not equal to minus converted number, then there is a problem. Okay, so you could say something like if random number is not equal to minus converted number, then there is an error. Okay, so this error should not come when I run. Oh, this EP wave will come. This I added now. So you can see that the error did not come. Okay, see, error came. Hmm. If random number is not equal to minus converted number, or random number plus converted number is not equal to 0. Hmm. This random number would have become 0, right? Okay. Sorry. So this we have to, you know, let us say store backup, random number backup. Okay. So we'll have to declare one backup because we are destroying that random number when we shift everything. So we'll need one more here. Okay. So this okay. Hey. Hmm. So you can see that the output will not have that thing. And let us remove this display also. So let it run quietly. Okay. So the verification engineers, you can display once in a while. Okay. But if you display too much, it becomes very difficult to debug. Okay. Now you can try some more test cases. Let us say we try 123 or 122, right? This time you will see that the output will not be there. That error output will not be there. Okay. So there is no error. So another way to say the same thing in system Verilog is assert. Assert that this is true. Random number plus backup. I'm sorry, random number backup plus converted number equal to 0. Okay. Else, see, I'm not sure whether there is a semicolon or I don't know that there is a semicolon. Assert that this is true, else do this. So this is called an assertion. Okay. An assertion means this is true at the end. So because our program is actually trying to convert a number into its 2's complement number, at the end the assertion is that the random number and the converted number when you add we should get 0.
Sir, your problem statement was the string length.
Hmm.
How many bits? More than 8 bits could be, right?
Yeah, I can change it. No, see if I
But
want
your
to.
random number you are ranging always.
No, I can change this range, right? I can change this. See, let us say define n to be you want 64 means you can put 64, right? And this will be n minus 1.
Even you hard code it like this while running for simulation, in
Hmm.
one shot you'll not get for each test case output, no?
I'm going to get like you can
We
see,
are
no?
given
See,
7 test cases. Can I get one by one all test case output
yes. Okay, I'll
in
show
one
you.
shot?
One shot means it will do one by one only, no? How can it do in one shot?
I mean, a 8-bit number, you are getting a
Hmm.
8-bit number, two's complement. I want,
Yes.
suppose second number also, can we give uh, and get that one at a time all print, all two's complement of 7 cases.
Yeah, I can do, no? What is the big deal? I can put a repeat loop here. Okay.
Okay, so can
See,
you
here
do?
I can say one big repeat loop. Suppose I want to say repeat begin. This dump, let us not do any more. So repeat 8. So instead of 122, let us do random range, right? So this, if you want, you can change it to some value, 55,000 to 55,000, okay? Something like that. Okay, some random number in the pretty large range, and all of this will be done, and then we can have one more end here. So we'll have to adjust the indent properly. Okay. So this is the first random number. Okay. If you want them to be printed, I will have them printed here, right? See, if you don't want this assertion, I can remove this assertion, and I can simply say display. Okay. So this hopefully will do. This end corresponds to outer loop, and this is our inner loop. This is our end inner loop. Yeah. And this is for initial. Okay. So we have to put it as signed, I guess, right? We have to put it as signed. Okay, this one, see, one mistake that I have made is this should not be 8, right? This should be 10. It should do a 64-bit. No, whatever. 64. Here we go. So this is n minus 2. Don't tell this is wrong. Somewhere else I have made some hard coding. So n minus 1. What is this? Bit sign -1 to 0. Suppose I try 16 and see. Does it work? Here, have I hard coded anything? I don't think there is any hard coding here. Here, there is some problem. Random number is guessed. Consider number is 0. Bitstream is random number of 0. The reset. We apply the quants.
Sir, U random can be negative, no, sir?
Yeah, yeah. U, I think, means uniform.
I
Uniformly
thought
distributed.
not unsigned.
No.
What do you mean by sir uniform?
Random numbers, no? Uniform and uniformly. In that range, any one number is uniformly. Now it's okay, I think, no? What did we do differently now? No, no, it's still not okay. The random numbers themselves are not okay. So my problem is this 2 to the power n minus 1. Mm. Okay, now it's working. Mm. I'm still displaying the wrong number here. See the Mhm. But why is this? Mm, when I send it to minus 16, sorry, n 2 to the power n minus 1, doesn't work. See, it closes. See, I have a feeling this U-random range has a limitation. It may not be able to generate. Let us try random, dollar random. Okay, random is another one. See, as far as I remember, dollar random is a 32-bit output. So up to 32, this will work. Okay, 13604. Okay, this is what you wanted, no, Professor?
No, sir. I was seeing that. Is that you are limiting, though signal length is more
Hmm.
than 8 bits, you are limiting your testing through 8 bit by making u random, giving minus 127 to plus 128. Sorry, minus 128 to plus 127.
No,
That
I
is
have
8,
removed that restriction now. See, I have gone up to, see, now
32
I'm
bit.
saying 2 to the power, where is it there? I have made it dollar random. Dollar random will give you from minus, it's a 32-bit random number. So I can go up to 32. Okay.
Sir, are you generating any hardware signal after 8 bit? We can
No,
detect that one.
no, I am not detecting any, I'm not hard coding 8 anywhere. You can check.
That's what
I'm not,
I'm saying.
I'm
But
not hard coding it anywhere. It is taking a
okay, sir.
32-bit number, right? See, I'm applying n plus,
Yes,
see, you can see, no? This 8 is
yes.
for the number of test cases. Okay, that also, if you want, we can,
Mm.
number of test cases.
And I remembered my question was
Hmm.
through you random you are giving random number, but you have asked few cases. No, I wanted exactly those cases.
That can also be
Can
done.
I
You can do that, no?
can I
Yeah,
put
you
in
can do
a
that.
array and
I showed you, no? Yesterday I showed you that. So, for example, I could make an array, no?
that
Suppose I say,
only I tried, but
yesterday I showed you, right? For example, instead of repeat num test, let us do for loop. For I equal to 0, I less than num tests, I plus plus. Okay. So I has to be declared here. And we can declare a random number array. Okay. And I think the way to initialize is like this. Okay. That is what I remember.
separated by comma.
Uh, so you can say 0, 1, minus 1,
Yeah.
23, minus 23,
Yeah.
plus 101, minus 123, plus 255, minus
Yes.
257. Okay, how many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9. Let us take one more. Okay.
Yes.
So let us take 10 tests.
Yeah.
Okay. And instead of generating random number using random, you will have to say random array
Mm.
of I. Okay. So this should do the same thing.
Oh,
Okay, this one is not giving the answer. Mhm. Hmm. Can anybody look up how to initialize? Just a minute. Oh, I'm sorry. This I have made a mistake. I had to say num tests. Okay, I'm sorry. I forgot that.
so-
Okay. Okay, let us try cadence simulator. Okay, so 600 minus 600, right?
Yes.
And then 257. Okay,
Yes, sir.
okay, sir.
Yes, sir. Yes.
Happy?
Yes, sir.
Happy. So let me give you this also in case this is a second version of the same thing.
Yes, sir.
All right.
Yes, sir.
Any other doubts? Anybody else has any doubts? Professor asked very good questions. Right. I'm very happy. Can you use star star in Verilog? Yes, you can use star star in Verilog. 2 to the power star star is 2 to the power, 2 to the 2 star star 4 means 16. Can you try it on minus 128 0? You want me to repeat this for 128? It will work, man. I think we have tested it enough. Okay. Okay. All right. Any other questions before we move on? So random number generation, we have been looking at that, right? We looked at what is it? Dollar random. Dollar random will generate a 32-bit random number. So maybe I can give a very trivial example. Module test, right? So you can say int x for or repeat 10, x is dollar random, and then dollar display percentage dx. Okay, so let us make it int signed or something like that. Okay. So if you run this, you will see that it will have random numbers in that range. Okay. So from minus 2 to the power 30 1 to 2 to the power 31 minus 1. That is a range of numbers that will be. Okay, or is it 64? I'm not
No,
very
sir.
sure. It may be 64 bits also.
Oh,
I don't
10,000.
remember whether dollar random is 64 bit or 32 bit. So you can check and see, right? I don't remember exactly. Whereas U random range is, it looks like it has some problem. It may have some limitation.
Sir, it will display in binary, it will give no number of bits, sir.
That is, it will display 32 bits because int is 32, right? So you can do it that way. If that is what you want, we can show. So maybe it is possible to represent such big numbers in 32 bit. So they look pretty big. Okay, so this is 32-bit, I believe, right? But that we should not be limited by such things. Okay, we should not be limited by these kind of things, right? So system Verilog has extended some of these things. Okay, the dollar random was only in Verilog. Verilog also had dollar random, right? And I think U random range was also there, right? But what is different in system Verilog is they have introduced this. See, suppose I want to define a random number which is let us say 16 bits, okay, and it is like our we did that exercise earlier, right? That 4-digit number. So suppose we call it as 4-digit number. So 4-digit number means it should be like BCD number, uh, 0000 to 9999. So these are the. So this is a class I want to create. Okay? Create a class of 4-digit BCD numbers. So the numbers will range from 0000 to 999. So we'll go ahead and declare, let us say logic or bit, whichever you want, bit 15 to 0 or bit 3 to 0 of digit 3, bit 3 to 0 digit 2, bit 3 to 0 digit 1. We could have done it like this only, D3, D2, D1, D2. Okay, so we have 4 digits, each of 4 bits, right? And what it allows you to say is rand. So this rand addition means that I will be requesting for random number generation. I mean, these things will be generated randomly. Okay. So let us take this example, and we can put a constraint. The constraint, the syntax. Let me recollect here. Constraint.
Inside.
Uh, Random constraints is from page 128. So let us go ahead and do 150, something like that. So these are the random constraints. Okay. So you can declare constraint has to be followed by any name for the constraint. Okay. So we'll call it BCD constraint. And here we have to say what is the constraint that we want. Okay. So I can say something like, whatever this similar constraint try to put. Okay. I can say D3 should be less than 10. Then D2 should be less than 10. D1 should be less than 10. And D0 should be less than 10. Okay. So these are the four constraints I have. You can also add things like D3 should be greater than or equal to 0. Okay, that is also okay, right? But I think the real constraint we want to add is that since it's a 4-bit number, 16 possible numbers can be put here, but we are putting that this is okay, so that is what it is, right? So later, if I create a module called test, here I can say 4-digit number, let us say something like secret. So we can initialize secret equal to new. Okay, and then secret dot randomize. Okay, so if you say secret dot randomize, that is a built-in procedure that will be valid for any class where there is a rand defined. Okay, so it will put random values into D3, D2, D1, D0 based on the constraints that you have provided. Okay. Then you can put dollar display secret dot D3 secret dot D2 secret dot D1 secret dot D0. Okay. And maybe we can do this a few times, repeat 25 times. Okay. So you will realize that it will constrain like that. The BCD numbers will be constrained. Okay. You can see that it is always keeping that constraint. So this makes my life simple. See, earlier if I had to generate a secret random number, right, it was not so easy. I had to go and myself check, right? Whereas here it's built in because I'm doing this. Is that clear?
Sir, you would have taken rand int, then you would have written greater than 0.
What do you mean by rand int? Like dollar random. What is the question, Professor?
Sir,
Hmm.
instead of bit, can you
Hmm.
declare int?
You can declare int. Yeah, you can declare int.
And that time we limit negative number, no, sir?
We are saying that then we have to add other
No.
constraints like it should be greater than or equal to 0. Okay. See, if you are in,
I'm thinking if it is int, it will take negative number also.
that's why I'm saying D3 should be greater than or equal to 0.
Sir.
Right? These additional constraints will have to be put.
Yes. Rand word will not be there, sir.
No, that rand is already here. Okay, this rand is already here.
Okay, sir. Okay, sir.
So this should do the same thing. This will also do the same thing. If you print them side by side, you will appreciate that it will look like a. I think we are allowed to say 1D and all that, right? 1D, 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 1D.
Generally, say 0D.
1D is also should be okay. So it is displaying them as 4-digit numbers. That okay?
Yes, sir.
So in our previous exercise, we wanted maybe I'll give this guys to. Suppose we wanted a 64-bit number or something like that. So we'll say initial. So we'll say first we have to declare that na random number 64 64, and that can be, I think here itself we can say, and then we can say R64 dot randomize, right? And then printf percentage B. I think LD maybe. I don't know how to print the 64-bit number. So this LD may print it as a 64-bit. It should be that R64.x. Okay. So you can see that it is printing it like this. We could have used this. I think we had some difficulty in running a 64-bit in the previous example. Okay. This may be the actual value. Any questions in this? You can have any number. Huh? You can say rand.
Sir, that 1D, once you tell me, sir. Percentage 1D.
As a 1-digit number.
0D andre, sir.
0D usually append zeros in the beginning if you want. Okay. Suppose the number is smaller, then zeros will be appended in the beginning. These things you can read, Professor. You don't need me to
Yes.
explain all this. Okay.
Yes.
These are not the kind of questions that I like to answer. Right? These are easy to find.
Yeah.
You ask some conceptual question in this, I'll be happy to answer.
No, I
The
was thinking
syntax
something.
questions, you should not ask. Right?
Okay.
It's not just for you. I'm telling everybody. Okay. Even you should say the same thing to your students. If your students are bothering you with syntax, tell them that is not. It's very easy in this day and age. Okay. So you can see that. I'm sorry, I forgot to put y. I think y is 3 bits. No, why is it percentage BLD percentage BLD? I'm a little worried. Y is coming as 64 bit. Any idea what could be wrong? Percentage B, percentage LD, percentage B, percentage LD, and these are X which are 64-bit long, but Y is only 64-bit long. Now it's okay. What was wrong with the previous one? See, sometimes the tools will have bugs, okay? So the previous one looked like a very buggy thing to me. See, now it's okay. Okay. But when I displayed it earlier, even now there is a bug. Can you see? X is 3 bits, Y is 3 bits, and X is actually 64 bits. But it is confused. It is printing like this. So this is a bug in the tool. Can you see? It's wrong. When they implemented this, something is not correctly implemented. It's okay. So we can. I think when I don't know what, there is some peculiar bug in the tool. All right. So you can create any number of random numbers. So what, for example, if you are generating some communication, see, sometimes people do communication projects, isn't it? They will define some network, right? See, they may declare some network of processors. So let us say this is 0 0, this is 0 1, this is 0 2, this is 1 0 1 1 1 2, this is 2 0 2 1 2 2. So we have 9 processors organized in a mesh fashion. So we may want to route packets from, let us say this is a source and this is a destination. And they may have come up with some way to route. See, for example, it could go this way. And there may be another time it may go this way. And sometimes it may take a longer path. So they have designed some routing algorithm. And the packets that they want to route will typically have the source and the destination and some maybe actual data. So they have to simulate 9 processors, and each of them may be sending data to a random destination. So the source, let us say this is my source, it picks one of the destinations as a random destination, maybe other than itself. So it may send to 0 0, or it may send to 0 2, etc. So this is where you need random numbers. Okay, but those random numbers have to have some constraints. For example, the destination should be of the form I comma j, where I is in the range 0 to 2 and j is in the range 0 to. And if this is the if my id is row and column, then ij should not be equal to rc. Ij should not be equal to rc, which means I should not try to route to myself. So these are the kind of constraints that you may have, right? And you can use that class that I described, right, to do what is called as constrained random number generation. Okay, and they have given a lot of variety. Okay, they have given a lot of variety in terms of generating these random numbers. Okay, so things like I want a 16-bit address and a 32-bit data, but I want to ensure that the last 2 bits of the address must be all zeros. Okay, this constraint is called word alignment. That means I only want addresses separated by 4. So 0, 4, 8, like that. Okay. So these are word aligned. Similarly, you can also use RAND-C. Okay. There they say that the random number will go through a complete cycle before repeating itself. Okay. In when you use only RAND, there is a chance that I have generated. Suppose I was looking for a 4-bit random number. Okay, So I may generate 5, and again I may generate 5, and then 7, 8, 9, and again 5 may come, right? So that is allowed in RAND. But if you say RAND C, then it will sort of cycle through the entire range of random numbers before returning back to the. So you can do such things. So RAND C is allowed. See, they have very interesting constraints. Okay, see this. I have declared an integer random number x, y, and z, and the constraint C1 says x should be in this set x 3, 5, or 9, 10, 11, 12, 13, 14, 15. These are the only numbers allowed. So x can be either 3 or 5 or 9, 10, 11, 12, 13, 14, 15. And then, of course, there are some more 24, 25, 26, up to 32. And y to 2y. See, x has a constraint which is dependent on y, and things like that. So it will maintain, it's like these are no more independent random variables. Okay, you may have heard about, when we talk about random variables, we talk about independent random variables, right? But here these are not independent anymore. So x is dependent on y and z. Here is another example. A, B, and C, but A is inside this set. So first select B and C, and A must be one of them. Okay, this is a straightforward one. Okay, C3 should be inside this set. You can also specify the distribution. Okay, if you say x distributed in this fashion means, see, the only values allowed are 100, 200, and 300. Okay. X can take on only 3 values, and the probability that it takes on 100 is 1 over 1 plus 2 plus 5. Okay. So the probability of 100 is 1 over 8. The probability of 200 is 2 over 8, and the probability of 300 is 5 over 8. So that is what this dist means. Okay. You may be interested in such things. Okay. Here also, see, 100, 101, and 102 are selected with probability of 1 over 8. 200 is selected with probability of 2 over 8, and 300 is selected with a probability of 5 over 8, right? And so on and so on. Okay, there are a lot of variations of all this. Okay, so you will see that a whole chapter has been written on this. Okay, so you have to read it when you need it. Okay, there is no point in reading every possible constraint right now, because unless you use it, what is the point, right? So you can define very complex constraints and generate constrained random variables. So there is a constraint C1 which says for each AI should be like this. And see, look at this. It is a dynamic array. Okay. And the constraint says that every element of the dynamic array must be in this range. And another constraint says that AJ should be greater than 2J. Okay. So both these constraints must be satisfied. Sometimes the randomizer may fail, okay, if you give conflicting constraints. Okay, for example, if I say constraint, y constraint, y should be greater than 0, and at the same time y should be less than 0. Okay, yeah, I have given a bogus constraint. Okay, it cannot happen. Well, let us say less than or equal to. Okay, no, even that is okay, right? It cannot be both greater than 0 and less than 0 at the same time, right? So you will see that this will fail. Randomize will fail. Okay, so you will have to check if random dot randomize is successful, then display. That is the correct way of using it. Okay, otherwise don't display. Okay, so it will say it's called failed. Okay, so there may be a way to make sure that it doesn't fail like that. I don't know. I mean, I had to search. See, maybe we really don't want to fail like that. We may want to just give a warning and come out. Okay, so figure it out. You can read the manual and
Sir,
then,
assert,
huh?
assert statement can we use?
No, no, no. Assert is slightly different, right? Assert means when you come to that stage, make sure that a particular condition is valid. Okay. Here, what I'm trying to say is, see, this is a terrible thing to happen. If your random number generation fails and it aborts, we don't want it to abort like that. We want it to go on, right? We should we should be able to say otherwise do something. Okay. Maybe otherwise we can set whatever different value I want to set. Okay. So unfortunately, it is not giving me that opportunity. Okay. So if I run this, unfortunately, that random number failure will cause it to stop. Okay. So sometimes I may want it to not fail like this, but want to continue. There will be some setting that you will have to use to say that don't fail. You will have to see, read the manual and figure it out. Okay. See, I am telling you something. When you join, you will not be, if you join a company, you cannot be told about everything. Okay, this is a very big manual. Then there is a UVM also, right? So they will not teach you every page in this manual. Okay, they may give you some 1 day, 2 day training. After that, they expect you to figure it out yourself. Okay, so the sooner you get into that habit, the better. Okay, so don't get into this habit of asking, every question. No, that is not going to work for you. Okay, all right. So we can give, you know, let me see if I can see in that cache. See, suppose you are trying to test a cache controller. See, remember we have been talking about this cache controller, right? We are saying that there are some 64 pages, and the memory address will be 16 bits. Okay, so 6 bits will indicate the page in which you are, and 10 bits will indicate the byte address. So suppose I want you to generate the list of addresses randomly. If you do uniform random distribution, unfortunately, what will happen is, it may generate a page 0 first, then it may generate 55, and then 44, and 12, and 9. So, in a way, it'll jump around. Okay, that is not how programs behave. Okay, see, programs show what is called as locality of reference. Okay, so what is locality of reference? After you fetch a particular instruction, you are very likely to fetch an instruction from the same neighborhood, right? After I have fetched this instruction, I'm very likely to fetch the next instruction. Once in a while, I may jump and go to some other, not like this, 0 to 55. This is all very bogus. If you try to simulate this, you are simulating a very, unlikely situation. So you must, generate the page addresses in such a way that after generating page 0, the probability of generating 0 again is very high, and probability of generating anything else is less, right? So it may go from 0, 0, 0, 0. Many times it will happen. Then finally we may shift over to 1. Then occasionally we may go back to 0. This is also true for data. See, in any image processing and so on, after pixel number ij, we are very likely to go to ij plus 1, etc., and they are usually located very in the same page, or at most in the previous page, or something like that. So you can think about how you will use random constraints to generate addresses like this. Okay, that is the kind of problem you will actually face. Okay, so you'll have to think about how to generate such addresses. Otherwise, your simulation may incorrectly declare that this policy is not good, or something like that, right? So you have to create a realistic situation during simulation, and then come up with some usually after simulation we want to know how many times misses were there, how many times hits were there. What if I change from LRU policy to something else? What if I change write back policy to write through? How many pages should I have? Should I have, instead of six, I'm sorry, 64 pages of 10 by 1024 bytes each? Can I have maybe 128 pages of half a kilobyte each, right? So these are the kind of things you try to study, right, during simulation. And if your generation of the input patterns is not realistic, then you are making incorrect decisions. Okay, so that is what happens, when you write your thesis, whether it's a master's thesis, PhD thesis, or whatever it is. You also, will show some simulation results, isn't it? So this is where you have to be very careful. Am I simulating a realistic situation, and am I coming to the right conclusion? Right? If you generate, it's easy to generate all kinds of random data, right? But then it is not, realistic at all. So that is the reason why they have provided constrained random number generation. Is that okay? Did everybody follow this? Did you guys understand this? So Bhola, Kumar, Om Nayak, they're all saying yes. Okay, so Dhruang Patel is saying yes. Good, very good, very good. So try that exercise which I told you, right? I want you to try this exercise. That is, I have this kind of a mesh situation. Okay, you can try to generalize if you want to. You can say I have a n cross n mesh. Okay, n rows and n columns, and I want you to write a way to generate addresses, okay, using these kind of constraints, that it should generate I to be in the range 0 to n minus 1 and j to be in the range 0 to n minus 1, and ij should not be the same as the row and column in which the processor is located. Okay. So I want you to spend maybe about 10 minutes right now and think about how you will do it. Okay. Think time.
जब गांधी पे ही मैंने दुकान खोले थे तो केक नहीं खोला होगा ना सब कितनी ज्यादा मेंटर
Mayank Roy Mandal,
शोरूम
please turn off. Please mute yourself. Mayank Roy. Mayank Roy Mandal, please mute yourself.
निकालो मैं देख भी नहीं रही और फीड में निकालो ना
So, how are things going, guys? Dhruva Shah has asked a question. Sir, there is a small doubt. What difference would a function, task, and module make in terms of logic implementation on hardware? Like, for example, when writing logic, if else creates a mux. No, no, you cannot have all these tasks and functions, etc. They may not be synthesizable. Okay, they are only for verification only. The Verilog code that you write must be very simple for the synthesis tools to understand. So if then else is okay, for while etc. are okay, but if you write all tasks etc., it will not understand. Those are meant for verification. So please explain how reverse bit works. You can label the bits in any way you want, man. See, there is no. See, something got happened. Something got stuck. See, module test. The reg 0 to 7 x, reg y to 0, 7 to 0 y. Okay. So if I write initial, let us say I set x equal to 55 and y equal to, or let us say x equal to 8h 55a and y equals 8h5a, right? and then for I equal to 0, I less than 7, I plus plus, dollar right, percentage B, x of I. Okay. So if I do this, what do you think will happen? Wait. See, there is no difference. You understood, no? Whether you call it 7 colon 0, 0 colon 7, there is no difference. Is it clear, Dev? It's your convenience. Some people like to call this as most significant, least significant bit, and they like to assign 0 to that. Okay. Whereas some people like to go this way. Okay. So it's convenience. So they didn't want to put any constraint on how you like to index the bits. Okay, some people are comfortable 0 to 7, some people are comfortable 0 to 7. You can put anything you want. You can say minus 7 to uh, minus 7 to what is it? Minus 7, minus 6, minus 5, minus 4, minus 3, minus 2, minus 1, 0. Okay, so you are allowed to do this also. Okay, here you can say I equal to minus 7. Okay, and I less than 1. Okay, this is also okay. Okay, so it doesn't matter. It's your convenience. That okay? So you thought it will reverse or something? Eh? No, it won't do anything like that. Hmm. So how is your random thing going? Random. So we could have a module called router or something like that. Okay. And what are the inputs? Its own row. Okay. Row, column. Then so let us assume that define the number of processes to be, let us say, um, 16, and num row will be square root of n, and define, sorry, define num column also will be square root of n. We assume that it is a perfect square, like 16, 9, etc. So here we may have to say bit and num row minus 1 to 0 is row. Bit num column minus 1 to 0 is column. So we have received the row and column number. Now this guy has to generate random addresses. Okay. So define a class maybe called packet, right? Which takes as input, we should define it here, which defines rand bit num row minus 1 to 0. This is a destination row. Rand bit num column okay. So we have these two, and there is some data. Let us say rand data size, let's say 256. Okay, so there is some data. So this guy has to generate, when it routes packets, okay, let us say packet or p. So p is a packet. So p is initially set to new, and suppose it generates 8 packets, right? So we have to say p dot randomize, and then it will write display um, %d sending a packet to %d. So row column it will put, and then it will also do p dot destination row, p dot destination column. Okay. And to test it, you will have to create a test module router test. So we could start with just one to start with. Let us say router. Let us say 1 comma 2, right? And we had to give some uh, Let's continue. And this is input, right? Then we can try cadence. Oh, this is square root becomes okay. So maybe I'll bring up something like that. To- mm, XX has come. Any idea why X's are coming here? This part is okay. The constraint I wanted to specify is constraint row column is the destination row is not equal to row. Destination column is not equal to column. Destination row should be greater than or equal to 0. Destination row should be less than num row. Then destination column should be greater than or equal to 0. And destination column should be less than num column. So these are my constraints. Hey, this row is not there, man. This row I have given. True undeclared. Huh? Why? True here. Any idea why row and column are not being understood?
Is it P dot row and P dot column?
No, no, no. Those are this row and column are right here. No, these are the row and column of the processor. It should be 1, 2. I have no idea why it's saying this. See? ओहो यहाँ पे है भाई. This is the point problem to say. Okay, yeah, right. So we'll have to create a okay. We'll have to create a function new column. But why row and column come as excess here? So the constraints are met. Okay. I don't think 1, 2 ever came. Okay, so it is making sure that the constraints are met. Oh no, 1, 2 came here. That means row and column are not correctly received here. Okay, 1, 2 has come here. So I'm clearly saying destination column should not be equal to column and destination row not be equal to row. So row and column. Say row and column are x's. I think I know. See, we should allow for little time because this guy initial will, so it takes a little time. So we have to give one unit here. Okay. So this is all not required. I think so. See, now it's okay. Okay. See, what happened was when router was created, time was 0, and immediately we are displaying, so as a result, the old value x's will be given. Okay, so this is a little curious bug. Okay, so you have to delay it by 1 unit so that by then row and column are available. Okay, all right, give this to you. Sorry, I took a little extra time today. I will close now. Did you guys get the idea why that percentage pound sign 1 was required? Because as soon as you start simulating, you don't have that value available. Any questions on this? Okay, sorry I took a little extra time today. Okay guys, I'll see you tomorrow.